In the past, we've developed various algebraic ways to find roots of functions. A root is where the function crosses the x-axis. We've also referred to these as zeros of functions or solutions to an equation where we set the function equal to 0. And a large part of algebra has been finding these roots, right? But sometimes it's very tricky to find these roots. So what Newton's method gives us is a non-algebraic way to find roots using calculus instead of algebra. Here's how it works. You start with some x naught close to your root. So we don't know what the root is, but we can get close to it. And that's important here because if you can't get close to the root and you start too far out, you'll go out the wrong way and you won't get to your root. This is an iterative process where we're going to get closer and closer to the root by just working our way in towards it. So you start with your x naught close. I'm saying the word x naught, N-A-U-G-H-T, but we denote that x sub 0. X sub 0 is almost always pronounced as x naught. Next, you follow that x naught up to the function itself. So there's f of x naught up there. And then you take the derivative at that point, which gives you a tangent line. You take the derivative and can compute the line and everything, which gives you a tangent line. Next, you trace that tangent line down to the x-axis, like so. This then gives a new point, x1, but note that x1 is closer to the root that we want than x naught, or x sub 0. So we then repeat the process. We follow x1 back up to the function. See, I'll just kind of make a dotted line here. Okay, there's the function at that point. And then we take f prime of x1. That gives us another tangent line, like so. It's kind of hard to see here. And then we follow that down. And here we go again, even closer, x2. Right, so we do this over and over, right? We find the point, follow it up to the function, take the derivative, follow that derivative back down to the x-axis, and repeat. Okay, so here we go up, like so, and you can see we're getting closer. Then we take f prime of x2, and so on. Right, f prime of x2 is going to take us right down here, and then we just follow this up, zigzagging until we get to the root. X in, right? Maybe it's 5, maybe it's 100. How do you know when to stop? Well, you stop when every iteration essentially gives the same value over and over, out to however many decimal places you want. So that's how Newton's method works in pictures. Let's bring it up in words and examine it that way. Okay, so here we go. The procedure, Newton's method for approximating roots of f of x equals 0. Okay, step 1, we choose an initial approximation as close to the root as possible. That's going to be our x naught. X naught. Okay. And then for n equals 0, 1, 2, 3, etc., this is how we find the next one. This is the whole meat of Newton's method. And there's a nice proof of this. It's not profoundly hard to prove. I won't do it here. It's in any calculus book. But it stems from the point slope version of a line. Y minus y naught equals mx minus x naught. So you manipulate this and you can arrive at this formula. What does this mean? Well, this says x sub n plus 1, so that's the next point on the x-axis. Next point is the previous point, is xn, previous point xn minus f of xn over f prime of xn. And all those xn's are the previous point. So once you find the next point, so to speak, that becomes the previous point, and you run it through it again, find a new point. Take that point, plug it back in, find a new point. Take that point, plug it back in, find a new point, and so on. When do you stop? Well, on to step 3, in the calculations when a termination condition is met, such as 2 points in the iteration agree to, say, 5 decimal places, or something reasonable. Right, so notice the difference between this method and using algebraic methods to find roots, right? This is completely different. It's very much a brute force method. Like, we're going to leave all the fancy algebra aside and just slowly walk our way in towards that root. So this is what we would call a very numerical approach, and there's an entire branch of math called numerical analysis, which uses this kind of essentially coding, writing small programs to do the calculus, and then letting the computer do the hard work. So let's look at an example of how we would use this to find a root. Okay, so these can look a little wordy just because there's a lot of things to say up front, but they're really not as bad as it initially looks. We have f of x equals x cubed plus x squared plus 1, and initial approximation x naught equals negative 1.5. Use Newton's method to approximate a root of f. Stop calculating approximations when two successive approximations agree to 5 digits to the right of the decimal point after rounding. Okay, so what this gives us is a function and a starting point. So here's the starting point, x naught equals negative 1.5. If this is not given, use some method to come up with it. You can just plug in a bunch of points and try to find a point that's close to the root. You can use some kind of graphing software and try to estimate where the root might be. But if it's not given, you just use whatever method you have to figure out where that first root's going to be. If you're too far away, this method won't work. You'll spiral out in the wrong direction. So it's important that you start close to the actual root that you're looking for. And then it tells us to stop when we have a certain amount of agreement. Okay, so let's remember the main part of Newton's method is this formula. X sub n plus 1 equals x sub n minus f of x sub n over f prime of x sub n. Okay, so we're given x naught. That's our starting point. We need to compute a few things. So f of x sub n, that's the function. So let's write this as, okay, well, we know what the function is. That's x n cubed plus x n squared plus 1. F prime of x sub n is the derivative of that. Okay, so 3x sub n squared plus 2x sub n. So we can combine these to give us x sub n plus 1 is simply x sub n minus our function xn cubed plus xn squared plus 1 over the derivative 3xn squared plus 2xn. And we plug in like this over and over, right? So x sub 1 is going to be x naught. Means we plug in x naught to all these, and that'll give us x1. So x naught minus x naught cubed, etc. Okay, and don't get too attached to this right now, because I'm going to use a different program to actually compute these. Because as you can see, computing these by hand is going to be a nightmare. But what we would do here is then plug in negative 1.5 for x naught to get x1. Okay, so there I've plugged in negative 1.5 every time there's an x naught. And you can imagine you can keep grinding through this on your calculator. You put that in, that'll give us a new value. And then you put that in for all the x's, grind that through, that gives us a new value. You're more than welcome to do that. People love firing up their calculators like this. I prefer to use an external program such as Desmos. So let's take a look at how that would look. And I'm going to do a split screen here with Desmos on one side and my document on the other side. So we already know, let's see, we already know what x naught is. So let's just get these going. Okay, we know x naught is negative 1.5. Okay, now I'm gonna put that function into Desmos here. So I'm gonna write this as f of x, and this will just save you a lot of time, equals, and there's tons of programs that would do this. Desmos isn't the only one. I'm gonna write it as f of x equals x minus the fraction up top. We have x cubed plus x squared. Use the caret key above the 6 to get to the exponent quickly. Plus 1 all over 3x squared plus 2x. Enter. Okay, now we can quickly get x1 by saying what is f of negative 1.5? What 5? Okay, and then we have it 1.466666. That value there that is giving us here, this in gray on the right hand side here, is then x1. Right? It's a little bit of a pain to put it in up front, but it's a heck of a lot quicker than using a calculator. So let's do, now we're in approximate here, approximately, I don't know, negative 1.4, and even this is superfluous, but it kind of follows what the question would want us to do, 6666666, I don't know, let's just say that. So now we need x2. All right. So instead of doing this again, like trying to cut off this 1.4666 somewhere, I'm going to do this. f of 1.5, negative 1.5. Okay, what this does is takes the output of f of negative 1.5 and plugs it back into the function. And look what we get. We get a new value that's assumedly closer to the root. So here we are with negative 1.46557. Okay, we'll say that for x2. Well, we're not agreeing to 5 decimal places yet, so we do it again. Well, then I'm going to go f of negative 1.5. So I'm taking the function and plugging it in a third time. And there's a bunch of ways you can do this. Oh, look at that. We get our agreement now. So this would be x3. x3 then approximately equals, again, negative 1.46557 after rounding. So now we agree to 5 decimal places on a new iteration, so that's where the directions told us to stop, because we have 5 decimal places of agreement. So we'll take x3 to be our actual root, 1.46557. And that's how the method works. So you can feel a little bit of the tedium involved in this kind of thing, even with the Desmos approach. And you can imagine with the calculator, a lot of things happen. You'll be cutting these off, and you introduce a little bit of error every time you cut those off to plug it back into the calculator, which is problematic, which is why I like to use Desmos. And then I like to use this kind of nested method to make sure I'm not cutting anything off when I plug in the value again. So really, we're just getting a taste of how we can use numerical methods to find roots. You can use numerical methods to do all kinds of things. It's a very different way of thinking about mathematics. If you like this, I recommend taking a course in numerical methods to find out about it. Actually, I recommend doing that even if you don't like it, because maybe you'll take the course and end up liking it. Either which way, it's a great thing to learn about. So give it a shot. I think the point of seeing this in a calculus class is just to be exposed to it and know that it's out there.